Natural convection. This topic discusses heat transfer that occurs due to fluid motion caused by density differences resulting from temperature differences. The main mechanism is buoyancy force, which appears when the fluid is heated and becomes lighter. This phenomenon is commonly observed in daily life, such as cooling of hot objects in air. Natural convection does not require fans or pumps to drive the flow. Understanding this concept is essential as a foundation for analyzing passive heat transfer systems. Lesson Plan: Heat Transfer. This slide shows the position of natural convection within the overall structure of the heat transfer course. This topic is built on the understanding of conduction and forced convection. The chapter sequence reflects a logical progression from basic concepts to advanced applications. Natural convection acts as a bridge between pure conduction and forced convection. This structure helps students see the big picture of heat transfer learning. Learning outcome. The learning outcomes describe the competencies to be achieved after studying this chapter. The focus includes physical understanding, derivation of governing equations, and use of dimensionless numbers. Students are also expected to apply Nusselt number correlations for various geometries. In addition, applications to fins and enclosures are important parts of the topic. With these outcomes, students are prepared to analyze natural convection systems independently. A hot egg releases heat to the cooler surrounding air through natural convection. The air near the egg surface becomes warmer. Its density decreases, and it moves upward. Cooler air then replaces the warm air, forming a natural circulation. This process continues until the egg temperature approaches the ambient temperature. This example shows that fluid flow can occur without any mechanical device. Natural convection of a cold drink. A cold drink absorbs heat from the surrounding air through natural convection. The air in contact with the cold surface becomes cooler and heavier, so it moves downward. Warmer surrounding air then replaces it. This circulation causes heat to continuously flow toward the drink. This example shows that flow direction is determined by density differences due to temperature. Ship buoyancy concept. The buoyancy concept explains why objects can float in a fluid. The upward force appears due to pressure differences caused by displaced fluid volume. For equilibrium, the weight of the ship must equal the buoyant force. The submerged volume of the ship adjusts to satisfy this force balance. This principle is also the basis for understanding buoyancy in natural convection. Volume expansion of substances. When the temperature of a substance increases at constant pressure, its volume increases. The magnitude of the volume change depends on the volumetric expansion coefficient of the substance. A substance with a larger coefficient experiences a more significant volume change. This density change is what triggers buoyancy force. This concept is the physical basis of natural convection. Check your understanding. This section is used to reinforce the relationship between expansion and temperature rise. The question tests whether the basic concept of expansion has been properly understood. The focus is on the effect of temperature change on volume change. This understanding is important before proceeding to convection flow analysis. Without this concept, the buoyancy mechanism would be difficult to grasp physically. Isotherms in natural convection. Isotherms show the temperature distribution in the flowing fluid. In laminar flow, the isotherm patterns appear smooth and orderly. In turbulent flow, the patterns become irregular due to strong mixing. The transition from laminar to turbulent is influenced by temperature differences and fluid properties. These patterns provide a visual representation of heat transfer intensity. Velocity and temperature profiles. The temperature profile shows the steepest gradient near the heated wall. The velocity profile is 0 at the wall, increases to a maximum, and then decreases again. The region where these changes occur is called the boundary layer. Inside this layer, viscosity and heat conduction effects are dominant. Understanding these profiles is essential for developing convection heat transfer correlations. Forces in boundary layer. A fluid element inside the boundary layer experiences several types of forces simultaneously. Pressure forces act horizontally due to pressure gradients. Shear forces act because of fluid viscosity and vary in the vertical direction. In addition, the weight acts downward as a body force. The balance of all these forces determines the acceleration and flow pattern of the fluid. Correct answer C. Pressure forces caused by horizontal pressure variations acting on the differential element. Explanation of incorrect options. A. Shear forces caused by vertical stress variations along the boundary layer. This is incorrect because shear forces act vertically and result from velocity gradients, not horizontal pressure variations. B. Body force due to the weight of the element's mass acting downward. This is incorrect as body forces act vertically due to gravity and are independent of horizontal pressure variations. D. Buoyant forces resulting from the difference in fluid density and gravity. This is incorrect because buoyant forces are not relevant to the pressure variation described in a boundary layer's horizontal direction. They pertain to vertical forces in fluid statics.
Franz Grashof, legacy. Franz Grashof was an important figure in the development of engineering and heat transfer. His name is immortalized in the Grashof number, which is fundamental in natural convection. His contributions covered mechanics, heat transfer, and engineering education. The Grashof number measures the relative importance of buoyancy and viscous forces. This concept is still widely used today in engineering analysis. Grashof number dynamics. The Grashof number represents the ratio between buoyancy forces and viscous forces. If buoyancy dominates, the convection flow becomes strong. If viscous forces dominate, the flow tends to be weak or suppressed. Heating the surface makes the nearby fluid lighter and causes it to rise. The flow behavior is strongly influenced by the value of the Grashof number. Convection heat transfer modes. Natural convection occurs when the flow is driven purely by buoyancy forces. Forced convection occurs when the flow is driven by external devices such as fans or pumps. Mixed convection appears when both mechanisms are significant. The comparison between Grashof and Reynolds numbers determines the dominant regime. This classification is important for selecting the correct heat transfer correlation. Natural convection correlation. The Nusselt number represents the ratio of convective to conductive heat transfer. The Rayleigh number combines the effects of buoyancy and thermal diffusivity. The relationship between Nu and Ra is usually written as Nu equals C Ra to the N. The values of C and N are obtained from experiments. This correlation is widely used in practical engineering calculations. Check your understanding number 3. This question reinforces the physical definition of the Nusselt number. The focus is on understanding that the Nusselt number compares two heat transfer mechanisms. If the Nusselt number is large, convection is much more dominant than pure conduction. This concept is important for assessing convection effectiveness. Without this understanding, the Nusselt number would be just a mathematical symbol without physical meaning. Lord Rayleigh's contributions. Lord Rayleigh was a major figure in physics and fluid mechanics. His name is used in the Rayleigh number, which is very important in convection analysis. The Rayleigh number combines the effects of buoyancy and thermal diffusion. This concept is used to predict whether convection flow will occur or not.
His contributions form the basis of many theories of flow stability and heat transfer. Empirical Nusselt number correlations. Different geometries have different Nusselt number correlations. Vertical plates, horizontal plates, cylinders, and spheres each have their own empirical relationships. These differences arise because geometry affects the flow pattern. The Rayleigh number range also determines the form of the equation used. Therefore, the correlation must always be selected according to the physical configuration of the problem. Natural convection on inclined plates is still driven by buoyancy forces. The buoyancy force can be decomposed into components parallel and perpendicular to the plate. The component parallel to the plate is what drives the flow along the surface. The inclination angle affects the flow strength and the heat transfer rate. Therefore, surface orientation becomes an important design parameter. Natural convection on horizontal plates. For horizontal plates, the flow pattern strongly depends on whether the hot surface is on the top or the bottom. If the hot surface is on top, the warm fluid remains stable and almost no motion occurs. If the hot surface is at the bottom, the lighter fluid rises and convection cells form. This difference in stability significantly changes the heat transfer mechanism. A simple orientation change can determine whether convection occurs or not. Natural convection over cylinders. For a heated cylinder, the fluid near the surface becomes lighter and moves upward along the circumference. The curved shape affects the distribution of velocity and temperature around the surface. The flows from both sides eventually merge at the top of the cylinder. This pattern is different from a flat plate because of curvature effects. The cylindrical geometry leads to specific heat transfer correlations. Correct answer B. Buoyancy, as the warmer fluid becomes less dense and rises along the cylinder's surface. Explanation of incorrect options. A. The curvature of the cylinder, which forces fluid to flow symmetrically upwards. This is incorrect because the curvature affects flow distribution and heat transfer, but does not directly drive the upward flow of warm fluid. The flow is primarily driven by buoyancy. C. Shear forces acting parallel to the cylinder's surface due to fluid viscosity. This is incorrect, as shear forces contribute to fluid motion near the surface, but do not account for the buoyancy-driven upward flow of warm fluid. D. External pressure gradients uniformly distributed around the cylinder. This is incorrect because external pressure gradients do not primarily drive the upward convection currents. Buoyancy due to temperature-induced density differences is the main driver. Radiation versus natural convection. In many cases, the magnitudes of radiation and natural convection heat transfer can be comparable. Therefore, both must be considered together in thermal analysis. Increasing surface temperature enhances both mechanisms simultaneously. Ignoring one of them can lead to significant calculation errors. A good engineering approach always considers all relevant mechanisms. Natural convection in channels. Inside a vertical channel, boundary layers develop along both walls. These two boundary layers eventually merge at the center of the channel. After that, the flow becomes fully developed with relatively stable profiles. The spacing between the plates strongly affects the flow velocity and heat transfer rate. The gap design becomes a key parameter in passive cooling performance. Heatsink design comparison. Widely spaced fins allow air to flow more freely. Closely packed fins increase surface area but can restrict airflow. This flow resistance can actually reduce cooling effectiveness. Therefore, fin design always involves a trade-off between surface area and flow accessibility. Optimization does not always mean adding more fins. Vertical finned surface design. The thermal performance of a finned surface is determined by fin height, thickness, and spacing. Vertical orientation helps strengthen natural convection flow. Air rises through the gaps between fins and carries heat upward. If the spacing is too narrow, the flow can be restricted. Therefore, geometric dimensions must be carefully designed.
Check your understanding. Number 5. This question emphasizes the relationship between fin spacing and flow resistance. The goal is to ensure that thermal design does not focus only on surface area. Flow resistance can become the main limiting factor in natural convection. This concept is very important in passive heat sink design. Good cooling requires a balance between geometry and fluid flow.
Natural convection for PCB arrays. Vertically arranged PCB boards can be cooled by natural convection. The spacing between boards determines how easily air can flow between them. The height and width of the boards also affect the flow pattern and heat transfer. If the arrangement is too dense, heat can be trapped. Mechanical and thermal design must be considered together. Convective currents in enclosures. Inside an enclosure, circulation flow forms due to temperature differences between the walls. Hot air rises along the hot wall and descends along the cold wall. The maximum velocity usually occurs near the center of the cavity. The shape and size of the enclosure strongly influence the strength of this circulation. Geometry becomes an important factor in closed system design. Convective currents in horizontal enclosures. The lighter fluid stays above the heavier fluid, and the system becomes stable. In this condition, almost no convection flow develops. If the hot plate is at the bottom, the lighter fluid rises, and the cooler fluid descends, forming circulation. The position of the heat source strongly determines whether convection occurs or not. Thermal stability is determined by the density stratification of the fluid. Conduction versus convection. In pure conduction, there is no fluid motion assisting heat transfer. When natural convection appears, fluid motion significantly increases the heat transfer rate. This is often modeled as an increase in effective thermal conductivity. The Nusselt number is used to measure how large this enhancement is. A large Nusselt number indicates convection dominance. Horizontal rectangular enclosure. Heat flows from the higher temperature surface to the lower temperature surface. Inside the fluid, heat transfer can occur by conduction or convection, depending on the conditions. The ratio of height to length of the enclosure affects the flow pattern that forms. If the space is very narrow, conduction may dominate. If the space is large enough, natural convection can develop strongly. Correct answer B. The aspect ratio of the enclosure, as dimensions L, H, and H influence heat transfer and flow behavior. Explanation of incorrect options. A. The density of the fluid alone as it governs the rate of convection or conduction. This is incorrect because while fluid density affects convection, it is not the sole determinant. The aspect ratio and temperature gradient play a significant role in heat transfer behavior. C. The external temperature gradient outside the enclosure affecting internal heat transfer. This is incorrect because the heat transfer within the enclosure is governed by the internal temperature difference, T1 and T2, and fluid properties, not the external temperature gradient. D. The thermal conductivity of the enclosure walls regardless of the temperature difference. This is incorrect because while wall conductivity might affect heat leakage, it does not determine the internal fluid heat transfer behavior, which depends on the temperature gradient and aspect ratio. Inclined rectangular enclosure. In an inclined enclosure, the buoyancy force is no longer aligned with the walls.
The inclination angle affects the flow pattern and convection cell structure. Heat still flows from the hot side to the cold side, but the flow paths change. The height and length dimensions still play important roles in determining flow intensity. This system shows that orientation affects thermal performance.
Critical angles for enclosures. For each aspect ratio, there is a critical angle at which the flow pattern changes significantly. The larger the H/L ratio, the larger the critical angle. At certain angles, the system becomes more stable or more efficient in transferring heat. The concept of critical angle is important for enclosure design optimization. This shows that orientation and geometry are closely related. Vertical rectangular enclosure. In a vertical configuration, heat flows laterally from the hot wall to the cold wall. Buoyancy drives the fluid upward near the hot wall and downward near the cold wall. This circulation enhances heat transfer compared to pure conduction. The dimensions H and L determine how strong the circulation becomes. This system is often used as a model for double-pane windows.
Concentric horizontal cylinders. Heat flows radially from the inner cylinder to the outer cylinder. In the annular gap, heat transfer can occur by conduction or natural convection. If the temperature difference is large enough, fluid circulation will develop. The inner and outer diameters affect the flow structure and heat transfer rate. Circular geometry produces behavior different from flat enclosures.
Concentric isothermal spheres. Heat flows radially from the inner sphere to the outer sphere. The space between the two spheres can experience either conduction or natural convection. The gap size and sphere radii strongly influence the dominant mechanism. If the gap is small, conduction will dominate. If the gap is large enough, convection circulation can develop. Check your understanding, number 7. This question emphasizes the medium through which heat transfer occurs between the two spheres. The focus is on understanding that heat must pass through the fluid in between. Without a medium, neither conduction nor convection can occur. This concept seems simple, but is very fundamental. In thermal analysis, all heat transfer processes always require a medium or a radiation field.
Nusselt number variation. Heat transfer can lie in the transition between natural and forced convection. The Prandtl number affects the strength of convection effects on temperature distribution. Experimental data show good agreement with theoretical solutions in different flow regimes. Variations in the Nusselt number reflect changes in the dominant heat transfer mechanism. Such graphs are used to select appropriate models in engineering calculations.
Natural versus forced convection. If the forced flow is aligned with the buoyant flow, heat transfer is enhanced. If the forced flow opposes the buoyant flow, natural convection can be suppressed. If the forced flow perpendicular, the flow pattern becomes more complex. This interaction strongly depends on whether the hot or cold surface is involved. Geometry also influences how the two mechanisms interact. Specific heat and thermal conductivity trends. Near critical conditions, specific heat can increase sharply. Higher pressure shifts the peaks of thermal properties to higher temperatures. Thermal conductivity shows similar trends, although usually less pronounced. This behavior indicates phase changes or thermodynamic instabilities. This understanding is crucial for designing systems operating near critical conditions. Correct answer, B. Peaks in specific heat near critical conditions indicate phase transitions, which are essential for designing efficient thermal systems. Explanation of incorrect options. A. Specific heat remains constant across all conditions, making it irrelevant near critical points. This is incorrect because specific heat varies sharply near critical conditions, highlighting significant phase transition effects critical to engineering designs. C. Thermal conductivity is unaffected by specific heat behavior, so only conductivity needs to be considered. This is incorrect because thermal conductivity often peaks in alignment with specific heat, and both properties are important for thermal system optimization. D. Carbon dioxide's thermal behavior is independent of temperature and pressure, simplifying critical condition analysis. This is incorrect, as carbon dioxide's thermal behavior is highly dependent on temperature and pressure, particularly near critical conditions where variations are pronounced.
References. This slide shows the main sources of the material and figures used in this chapter. The primary reference comes from the Chengel and Gahar textbook, which is an international standard. This confirms that the entire discussion is based on well-established engineering literature. Using strong references is important to maintain scientific accuracy. This material can serve as a foundation for further study and research.